Oh well. Welcome to Lesson 7 in CP Java, where today we're going to be talking about recursion. So what is recursion? Recursion usually is a function that calls itself. So within the function, you'll have like calls of that function inside of itself. It's useful for problems. It's useful for defining a problem in smaller terms of itself. So like breaking down problems. And so usually recursion requires you to find the smallest problem or the base case, and that'll help you solve a question using recursion. And each branch in recursion, as like image here, they use like branches to represent each recursive loop. They branch out into 3 more branches or however many more. Each triangle is made of 3 triangles out of each of its sides. So in here, you have the recursion of each triangle like sticking out of each one, and then you just continue doing that and you'll get this shape. So what is the problem in this code? All right, you in your main you call fun, and then in the public setting void you call fun again, and this is not what you want. This is gonna like infinitely call itself over and over again, and that's not good, right? So that's a problem you don't want to run into while using recursion. So now, little problem: calculate the sum of numbers in an array. So here's an iterative algorithm, and basically you loop through with a for loop like you usually might. You go from you add up all the numbers in this array and keep track of it using sum. So each loop you'll go up 1 index, adding first loop you'll add 1, second loop you'll add 5, and then so on and so forth. And you can solve this using recursion like this. So instead of using a for loop, you have public static int sum. So you just add up you just add up everything in the array using the function sum. And so you pass in your array and your array.length minus 1. And so if I equal to 0, then return array I. So basically, this is the exit case, which allows the recursion to exit itself, so you don't get that infinite recursion. And if I is not equal to 0, then you return sum array I minus 1, and you add array I to add the current element. And so basically, I is to control where you are in the array, and the array is just always the exact same array you pass through. So I hope you understand that. I hope that's not too confusing. Okay, so here's a little visualization. So sum array and 3 is equal to sum array 2 plus array 3. So yeah, it's basically just the return statement. And then you call sum array 2, and that'll lead to sum array 2, and then you'll go into the return statement, and it'll return sum array 1 plus array 2, and then you go to the return statement again. Sum array 1 is equal to sum array 0 plus array 1, and so because you hit 0, you're going to go back up. That was actually cut out, but it was there in the previous code. I can show that after. Now you go back up. Sum array 1 is now equal to array 0 plus array 1, since this returned just array 0. And so this one is array 0 plus array 1 plus array 2, and go up one more time. Now you get array 0 plus array 1 plus array 2 plus array 3. And so here's something you can do for practice. So calculate factorial n, right? And factorial is like that exclamation mark thing, which equals to 1 times 2 times 3 times whatever till times n. So what is the base case? Does anyone want to take a guess? When n equals to 1. Good. Yes, when n is less than or equal to 1 in case you have like any bugs. But yeah, that's the right base case. And so what does anyone want to guess what you return? Yeah. Return factorial minus 1 times n. Yeah, basically. Yeah, good job. There was actually a little hint there that I didn't. I forgot that was there. Oh well. Good job. You guys did it anyway. They're smarter than we think. Well, actually, no, not really. You guys are very smart. Good job. So here's another case, right? Find the biggest number in the array, or the maximum number in the array. So what is the base case in this situation? All right. Yeah, basically, when your index turns to 0, and so then you return. And then what would you return here? Wait, that's the exact Ryan. Okay, ignore
I just
this.
copy pasted.
Yeah, ignore this. This is wrong. But what should we return in this situation? Yes. Think long and good about it. Math.max AB returns maximum of AB. Yes. Or you can use ternary operator. But we haven't learned that. It's basically short if. Math.max Aaron. Yes. That is precisely. Good job. That you did. And then you just call it again. Recurse itself again with math.max. So you just compare it to every single element in the array. But yeah, that is the gist of it. Good job. Okay, Ryan.
I'll start screen sharing from here.
Okay.
Yeah. All right. So let's tackle a fun problem. Is this a palindrome? How can palindromes have anything to do with recursion? So what is a palindrome? Well, a palindrome is a word that reads the same way forwards and backwards. Do you guys have any examples of some palindromes that you like? You can put them in the chat. Any palindromes you can think of? Well, I have taco cat over there. Mom, yeah. That's a good one. Right. Dad, lol. Yeah, lol. All right. Okay, so those are all valid palindromes, right? So let's write a program to determine if a word is a palindrome. So how is a palindrome formed, right? Well, we can always check. We can loop from the front and the end and then check like if the front and the end are the same, and then we can use pointers to go towards the middle of the word, right? That would be a way to do it with a loop, but let's consider what could be the base case for a palindrome, right? So if you think about the most trivial case, right, is that a string is a palindrome if it's empty. Because if a string is empty, then it pretty much reads the same way forward and backwards. It's just empty. And a string is a palindrome if it consists of only one character. So it reads the same both ways because it's X, like no matter how you read that. And then here's the more tricky case. Think about this. A string is also a palindrome if the left and right ends are the same characters and there's a palindrome in between. So you can kind of see the recursive property. A palindrome is a palindrome if the first character and the last character of the word is the same, and everything in the middle is also a palindrome. So you can kind of see the recursive property here. There's a palindrome within a palindrome within a palindrome, right? So you can kind of see how you can do those recursive calls. So for example, dad is a palindrome because both ends are D, and A is a palindrome because we've established that a single character is a palindrome, right? So dad must be a palindrome because it has a palindrome in the middle and the N is D, and D are the same letter, right? Like, what about taco cat? Well, taco cat is a palindrome because the N is a T, the beginning is a T, and ACOCA is a palindrome. Well, how do we know if ACOCA is a palindrome? Well, we're just going to apply the same function again. We're going to compare A and A, right? So a coca is a palindrome because A and A are the same, and COC is a palindrome, right? How do we know if COC is a palindrome? Well, C and C are the same, right? And let's check if the middle of C and C is a palindrome. Oh, wait, it's only one character. What do we know? Well, we know that one character is obviously a palindrome. So then we know that's true. So if O is a palindrome, then COC is a palindrome. If COC is a palindrome, then ACOCA is a palindrome. If ACOCA is a palindrome, then taco cat is a palindrome. So you can kind of see this kind of recursive kind of thinking, right? Let's apply it to a couple of ones that you guys proposed, right? That are more appropriate. Like you said, poop is a palindrome. That's true. So poop is 4 letters. Well, poop, like the first letter is P and the last letter is P, right? So is it a palindrome? Well, it depends on if OO is a palindrome, right? Is OO a palindrome? Well, it depends on empty space is a palindrome, right? Because O and O are the same. And then let's check if that empty space is a palindrome. Well, an empty space is a palindrome because that's our base case. So we return all the way up, right? Then OO must be a palindrome. If OO is a palindrome, then poop is a palindrome. Is mayonnaise a palindrome? I don't know.
No, Patrick, mayonnaise is not a palindrome.
Yeah, so, well, you guys can check that once you guys know the algorithm. But I appreciate your sense of humor. So you can see that any case that's not covered by the first 2 cases can be described with the third case. So that's what you need in a recursive algorithm. You need a base case, so like the trivial cases, which is an empty string, and if there's 1 letter, right? When you have 2 letters, you can already use the third rule because like the first letter is equal to the second letter, and there's empty space in between, which is defined by the first case, right? So that's what you want to do when you're determining a recursive algorithm. You want to determine base cases and determine an algorithm that would define all of the other cases. So let's do some practice. Let's determine if something is a palindrome. So what would be the base case here? So remember, we're trying to go towards the middle, right? And I have a left index and I have the right index of a string. So what would be the base case here? Remember, our base case is when there's 0 or 1 character. Yeah, so 0 and 1 character. And how do we check if there's only 0 or 1 character left? So we have a string, we have the left index and the right index that we're checking. Yeah, so if dot length is equal to 0 or 1, I just condensed it into one statement, which is if r minus l is less than or equal to 1, then we will return true because we know an empty string and a 1 character will always be a palindrome, right? So what do I return here? This is the tricky part. This is why the block is like 4 lines long. So it probably uses some kind of if statement. I return different things if the outcomes are different, right? So if char at 0 and char at length, if the length at L and at R are the same, right? Char at L and char at R is the same, then what do we check? Then what is it dependent on? So I know the first letter and the last letter are the same, right? So what does, how do we determine if it's a palindrome then? Return is palindrome 1 str length minus 1. Exactly. So that is correct. And otherwise, what do we return? If the first character and the last character. Yeah, false. Yay, you guys got this. Now, if the char at L is equal to char at R, then we're making the problem smaller, right? We're incrementing the L and we're decrementing the R. So eventually, no matter how long your string is, it's going to get smaller and smaller. L and R are going to approach each other. And at some point, it's going to be less than or equal to 1, where we return true. So we know that it's not like an infinite loop. It's reducing the problem into a smaller problem, right? By moving L and R closer together. And if L and R are not the same, then we would just return false. So good job, everyone. You guys know how to check if a string is a palindrome using recursion. And now you see why recursion is so powerful. It's because you only need to know the concept. You don't need to think about how I'm going to use a loop to do this. You just need to identify the base case, so the trivial cases, and you keep drawing longer palindromes and longer palindromes until you find a rule or a pattern where you can write this recursive algorithm, right? Or the third rule in this case, right? Okay, good job. So let's go to some more complicated things. So here you see that we are only making one recursive call, right? We're using the function to just call itself, but with parameters that get closer and closer together or get reduced towards the base case, right? So what happens if we're using multiple recursive calls, right? How does that change? Well, we're going to calculate the nth Fibonacci number now. So what is a Fibonacci number? Well, you might learn in math class, Fibonacci numbers is that the nth Fibonacci number is the sum of the two Fibonacci numbers before it, right? So the third Fibonacci number is equal to the first Fibonacci number plus the second Fibonacci number. So the 0th Fibonacci number is equal to 0, right? So that's just how it's defined. It's not following any rules. Someone just decided, oh, the 0th Fibonacci number is going to be 0, right? There's no computation here. And someone said, oh, the first Fibonacci number, I would like it to be 1. All right, so what are the rest of the Fibonacci numbers? Remember, the nth Fibonacci number is the sum of the two Fibonacci numbers before it. So what is the second Fibonacci number? Anyone know? Yes, it's 1. Okay, let's see who can do quick maths here. What's the third Fibonacci number? 2, yes. What's the fourth Fibonacci number? 3. All right. So I think there's some mathematical formula that would help you calculate this, but I think it's very complicated. So you could probably just write a program to loop through it. But now you're thinking iteratively. What we did here was we were thinking about starting off from 0 and 1, and we're looping, right? We're determining the second one, we're determining the third one, we're determining the fourth one. We're going from the bottom up. And that is iterative kind of thinking. So you can see here, n equals 5, because I want to find out the fifth Fibonacci number. I have an array to store all of the results, right? So this is to store what's the 0th Fibonacci number, what's the first Fibonacci number, etc. So the 0th Fibonacci number is 0, and the first Fibonacci number is 1. And I can, starting from 2, I can start using the previous numbers to calculate the next Fibonacci number. So the I Fibonacci number is equal to the I minus 1th Fibonacci number and the I minus second Fibonacci number. So it's just the sum of the previous two Fibonacci numbers. And I'm using a loop to iterate through this. And I'll never miss a Fibonacci number because minus 1 and minus 2 will always have been calculated in a previous step, right? And I'll just print out what's the nth Fibonacci number. So this is probably very straightforward. This is probably what you would code, right? But let's think about how we can use recursion to solve this. Okay, so what is the recursive algorithm? So if I say fib at n returns the nth Fibonacci number, then how do I write this in a code? How do I express this in code? Fibonacci at n returns the nth Fibonacci number. Okay, Hank said if n equals 0, return 0, else if n equals 1, return 1, else return Fibonacci n minus 1 plus Fibonacci n minus 2. And that is correct. Wow, you're even ahead of all of the points that I put here. Yeah, so Hank is right. What is the base case? Well, think about what you needed to calculate the Fibonacci numbers when we were doing it iteratively using a loop, right? I only needed to know the 0th and the first Fibonacci number to use a loop to calculate the rest. So whatever I could do with a loop, I can also do with recursion, right? I only need to know the 0th and the first Fibonacci number. So therefore, those are my base cases. I don't have any more base cases because when I was doing it with a loop, I didn't need any more information. So I know that if I pass in 0 as a parameter, my answer is 0. If I pass in 1 as my parameter, I'm going to return 1. And how can I be sure it's not infinite recursion? Well, think about it. If I'm doing fib at n, if I do fib at 0 and I return 0, and if I do fib at 1 and it returns 1, the smallest n that would trigger a recursive call is n equals 2, right? Like, think about the loop. When do we have to start calculating Fibonacci numbers? It's at I equals 2, right? So therefore, the smallest n that would trigger a recursive call is n equals 2, because otherwise we would just return the number. Well, that would just call f at 1 and f at 0. So I can't get any smaller. I can't have a negative n, right? Unless you actually pass negative n into the function in the very beginning, then that would just be tragic because you're just going to have infinite recursion. But usually in competitive programming problems, they won't give you that kind of edge cases. They won't give you like negative Fibonacci numbers just to like trick your program, right? They will usually say the constraints, like n has to be equal or greater than 1, and you don't have to check that. You can assume that they're correct, and the test data is not wrong. All right. Okay. Oops. Well, you guys can go to see the code now. Try Fibonacci at 100. Why is it so slow? I'm going to paste the link of this. And I want you guys to try it out. Put some big number, preferably greater than like 50. Wait, it doesn't work? Oh, so did you guys try it out? Yeah, I'll just see if this works, okay? So let's try some low numbers. Let's be fair to our replit, okay? Let's not tax their server a lot, and let's input some small numbers. Did it like run forever? Like it's still calculating it? Yeah, it's still running, right? So let's try it out. Let's try it out. Wait. Does anyone have any ideas why it's not working? Why it's still running? Is it because there's an error in the code? Because I'm calculating so many numbers. That's correct. But when we were doing it with loops before, why didn't it take so long? Why are function calls being so time consuming? Is it because calling a function is slow? Is it because I'm making very unnecessary calls? Well, that's not the reason. You should still be able to run it if it's a decent program. So is this a decent solution? Think about before. Before we only had one recursive call, right? Here we have two recursive calls. Think about what happens if they overlap, right? Yeah, Eric, it can be very like bad time complexity with this code, right? So let's explore why it's so slow. Well, this is a recursion tree, so it shows all the method calls that you do. So for example, if I call fib at 6, I'm calling 5 and 4, right? And then if I'm calling fib at 5, I'm calling 4 and 3, right? So you see like how this recursion tree works, right? 5 calls 4 and 3, 4 calls 3 and 2, right? 3 calls 2 and 1, right? 2 calls 1 and 0, right? So this is a recursion tree. What does K stand for? Oh, like with the Intel chip? Yeah, I don't know. So f at 4 called 2 times, right? F at 3 called 3 times, f at 2 called 5 times, and f at 1 was called 8 times, and f at 0 was called 5 times. There's actually a pretty cool pattern that I can't explain myself, but you can see this is a Fibonacci sequence, the number of times your function is called, right? Right, so you're seeing like the same function with the same n is being called multiple times. So how do we fix this? How do we make sure a function is not called like multiple times? How can we make sure we don't keep recalculating the same answer? Store the value once you've calculated it. Exactly. Wow, you guys are very advanced minded. Yes. So remember in the iterative algorithm, we were storing the previous results, right, in our array. We can do the same thing with recursion to make sure that we don't calculate the same thing again. Like you can see that if this follows the Fibonacci sequence, your number can grow pretty quickly, right? You can have, even with f at 100, you see your computer was running it like forever, and it might run it for a couple hours. So how can we prevent calling the same Fibonacci at n again, or at least calculating it multiple times? Well, we can use caching, which was what you guys described. So whenever fib at n is called for the first time, you want to calculate and store the answer in dp at n. DP might sound like random letters to you, but it stands for dynamic programming, which is a concept that we're just going to do like a short introduction into, and we're not actually going to spend a ton of time into because we simply only have 2 weeks before the CCC. But it's basically, dynamic programming is like caching, right? You're storing the results. You're trying not to recalculate the same results again. So if Fibonacci at n is being called again, return dp at n instead of recalculating it through recursive calls. So you can see here, I say if dp at n is not equal to -1, return dp at n. So -1 is just what I assign to every element of the array to begin with. And -1 is just a nonsense number. -1 is just to tell us that we've never calculated this answer before, right? So if it's not equal to -1, we know that we've calculated the answer before and we've stored a replacement answer in dp at n, right? So if dp at n is equal to -1, we know that we haven't calculated that before. So if dp at n not equal to -1, so if we've calculated it before, return the array element. Else, if n equals 0, well, that was our base case, so return 0. If n equals 1, which was our other base case, return 1. Otherwise, we return dp at n equals Fibonacci at n-1 and Fibonacci at n-2. And this is just short form notation. This means assign the answer to dp at n and return the answer. So this is just short form. If you're confused about this notation, I store the result in dp at n and I return the result. So therefore, if I call the same n again, I could just return the array element, and I wouldn't call n-1 and n-2 again. And you can, in our next slide, you can see how powerful that is. So we have improved recursion. So this is our dp array, right? First, it's all -1, which means We haven't really calculated any answers yet. So we start off at Fibonacci at 6. So what is Fibonacci at 6 equal to? Don't give me the actual answer. Just write it like in terms of Fibonacci at n. What is Fibonacci at 6 equal to? Fibonacci at 5 plus Fibonacci at 4. Precisely. Fibonacci at 5 plus Fibonacci at 4. Well, which side does it go to? Which side does it go to? What's the next Fibonacci that's going to get processed or calculated? Would it be Fibonacci at 5 or Fibonacci at 4? So our return statement looks like this. Return fib at n minus 1 plus fib at n minus 2. Andrew is right. The n minus 1 is going to get called first. So Fibonacci at n minus 1 has to be calculated before Fibonacci at n minus 2 is calculated, right? So all the processes have to finish in Fibonacci n minus 1. So let's keep going. Fibonacci at 5 is equal to Fibonacci at 4 plus Fibonacci at 3. It goes to the 4 because 4 was called first. So everything in 4 must be resolved before Fibonacci at 3 is called. So Fibonacci at 3 plus Fibonacci at 2. Fibonacci at 3 is Fibonacci at 2 plus Fibonacci at 1. And Fibonacci at 2 is equal to Fibonacci at 1 plus Fibonacci at 0. You're already seeing how some are being called multiple times, like Fibonacci at 2 is being called twice, right? Well, what do we do here? Well, we've hit 1. Well, 1 is a base case, right? So let's consider Fibonacci at 1. So has Fibonacci at 1 been calculated yet? Well, no, it hasn't been calculated yet, right? So what do? Well, we calculate it by just returning 1 because that was our base case. And we store the result in the array, and we return 1 to Fibonacci at 2. And Fibonacci at 2 says, oh, Fibonacci at 1 is done. Let's calculate Fibonacci at 0. So has Fibonacci at 0 been calculated yet? Well, no, because it's -1 in the array. So I will put 0 in there because that's our base case. I don't have to calculate anything. Return 0. Well, what's Fibonacci at 2? Has it been calculated yet? Nope. So let's calculate it and put it into the array, and let's return it. And so on and so on. Calculate Fibonacci at 1. Wait, has it been calculated yet? Yes. So what I do, I just access dp at 1, which is 1, and I return it. Think about like all the recursive calls I'm saving at this moment, right? Has Fibonacci at 3 been calculated yet? No. What do? I calculate it, which is 1 plus 1, right? I store the result 2, and I return it. Well, Fibonacci 4 says, oh, Fibonacci at 3 is done. Let's calculate Fibonacci at 2, right? So has Fibonacci at 2 been calculated yet? Yes, just return the array element. And we keep going. Fibonacci at 4 hasn't been calculated. Calculate it, return it. Oh, wait, Fibonacci at 2 should return 1. Sorry, this diagram was wrong. But the answer is right. You return 3. And has Fibonacci at 3 been calculated? Yes. Access the array element, return it. Fibonacci at 5 calculated? Nope. Calculate it, store the result, return it. Has Fibonacci at 4 been calculated? Yes. Access the array element, return it. Whoa, we're done now. You see that this tree looks incomplete compared to the previous gigantic tree that I showed you. Because Fibonacci at 4 creates a ton of recursive calls, right? It calls Fibonacci at 3 and Fibonacci at 1. Well, we don't have to do that anymore because we already returned the answer. And return just kills like the function, right? So we basically chopped down like a huge part of the tree. So if you use this strategy, well, you're going to come up with the answer. The answer is just at dp at 6, right? So this is an inspiring dynamic programming quote. Dynamic programming is to describe the previous processes of saving your answer, right? So the quote is, those who cannot remember the past are condemned to repeat it. And it's by the dynamic programming, right?
Wait, who's dynamic? Is that like a real person? Like his first name? Is dynamic programming a real person? Because usually quotes are said by real people.
Yeah,
so his first name is dynamic, last name programming. So that means his parents are Mr. and Mrs. Programming.
Yeah.
And that means the father's parents before are also named Mr. and Mrs. Programming.
Yeah.
So there's like an entire family tree based on like programming?
That's an interesting point. Okay.
And what about the name of the father? Is the dynamic like named after the father's father, so he would be like dynamic programming junior?
Yeah, dynamic programming the third, dynamic programming the fourth. You know, like recursion, like a family tree, you know, goes down.
Okay.
No, dynamic programming is just a concept that some computer scientists created. But it would be cool if someone's name was actually dynamic programming, right? It would pretty much be.
Nah, he would probably be bullied if his name
Yeah.
was dynamic.
All right, so moving on, let's look at a dynamic programming question. So if you go on Dmod, you search up a question called frog1, right? Because there's frog2 and frog3. You guys can check it out, but it's more complicated. So basically, I have this Mr. Frog right here. And Mr. Frog wants to jump all the way to the last stone. And these stones have various heights. The first stone is 10 centimeters high. The second stone is 30 centimeters, 40 centimeters, and 20 centimeters high. And Mr. Frog over here wants to jump all the way to the last stone using the least cost. So his cost might be like his energy, for example, right? If he wants to jump from the first stone to the second stone, the amount of energy he needs to use is 20 units, 20 joules, whatever, just 20, right? And if he wants to jump from the second stone to the third stone, it would be 10 because the absolute difference of 30 and 40 is 10. So you kind of get the idea, right? So how do we know what's the best way to jump from 10 to 20? Well, you can say, let's calculate all the combinations, right? So let's take into account all the paths that he can take to reach the last stone. But you can see when there's also overlapping solutions as well, right? If I jump from the first stone to the third stone and the third stone to the fourth stone, I can use the third stone and the fourth stones like cost, like again, right? Like there are some overlapping problems within here. So how can we do this? How can we store the results, right? Well, we can store them into an array, for example. So every array would be like the first stone stores like dp at 0 equals the lowest cost to reach stone 0, right? dp at 1 would store, well, the minimum cost to reach stone 1. dp at 2 would store the minimum cost to reach stone at 2. And dp at 3 would store the minimum cost to reach stone 3. So you can kind of see how we can use dynamic programming to solve this, right? And how we can use recursion to solve this. So in order to reach stone 4, I can come here from stone 3, and I can come there from stone 2, right? So those are the two possible paths. And I can use a recursion algorithm to do this. So let's take a look on how we can solve this. So first, I would read in the number of stones, and I would have an array holding the heights of each of the stones, right? And I read the array. So HII equals int.nextInt. I have a dynamic programming array where I cache all the results. So dp at I would mean the lowest cost to reach stone I from the very beginning. And dp at I would equal -1 because I want to make sure that if I've never updated the value, then it's -1. So I know when to calculate using recursive calls and when to just return the array element, right? And then the answer would just be f of n minus 1. I'm just passing h and dp into it because I want to read those arrays. If you actually want to be a little bit more efficient, you can declare them as static variables and put them outside, right? But this is just a demonstration. So f at stone means the lowest cost to reach stone from the very beginning, right? So if stone equals 0, well, I'm just going to return 0, right? And like the lowest cost to reach stone 0 from stone 0 is 0. The frog would just not move. Therefore, it doesn't need to use any energy, right? So that's a potential base case. Well, if stone equals 1, well, that's just the difference of heights between the first stone and the 0th stone, right? It's just very trivial. What about if stone was 2, right? Well, we recognize that we can reach stone 2 from either stone 1 or stone 0, right? So stone 1 would just be stone minus 1, right? So f at stone minus 1 plus the difference between the stone at 1 and the stone and your current stone's height, right? So this means the lowest cost to reach stone minus 1 plus the cost to reach the current stone from stone minus 1. Whoops. And we can also reach it from the second stone, right? Like the stone further back, which is stone minus 2. Well, what's the minimum cost to reach stone minus 2? Well, it's f at stone minus 2, right? So the minimum cost to reach stone minus 2 plus the cost to reach stone from stone minus 2. So we're kind of like building up the algorithm here. It's the best result at stone minus 2 plus the cost to reach stone I from stone minus 2, and also from stone minus 1 plus the cost from stone minus 1 to reach stone, the current stone. So we want the minimum of both of these answers, right? There are only two ways to reach the current stone, which is from the stone immediately before it and the stone that's two stones behind it, right? So it's either stone minus 1 or stone minus 2, right? And we want to take the minimum of both of them because we want the minimum result. If I wanted to take the longest time to reach the current stone, I would do math.max, right? I want the maximum results of all the possible paths to reach the current stone. And I would just save the result in TP at stone, and I just return it. So this is kind of like the Fibonacci thing. I save the results. And if CP at stone not equal to -1, well, it just means that I've calculated this before. I'll just return the result over here. So does everyone get it? So the trick is to identify all the ways to reach the current stone, which is only from n-1 or n-2, right? And think about the transition. Think about what kind of cost do I need to travel from stone minus 2 to the current stone, right? What kind of costs do I incur by going from stone n-1 to stone n, right? And then you would take the minimum of both of those answers and store them into dp at stone, because that would be your current answer. The minimum cost to reach the current stone is the minimum cost to reach stone -1 plus the cost, and the minimum answer at stone -2 plus the cost to reach stone. So yeah, so that's how you can use recursion to solve a problem. And if you use dynamic programming, which means storing your results in a caching array, you can improve the performance by a lot, and your program will not TLE. So these are some practice recursion problems that you can do, right? So for example, let's just solve this question. This is called sumac sequences. This is CCC 2011 Junior 3. Just by a show of hands, or just type it in the chat. Are you doing junior or senior? Are you guys mainly doing senior or junior problems? You're doing senior? Senior? Yeah, makes sense. Usually like upper years do more senior, or if your programming skills are really well, you can do senior. Tried to do senior last year, but failed miserably. Yeah, it's fine. I mean, it takes a lot of time, like, and it's also highly dependent on like the contest problems, right? Last year I only got 28, and I was pretty disappointed, right? If you're in grade 12, I would highly recommend doing the senior, because on the Waterloo AIF, it'll ask you in grade 12, are you planning to write the senior contest? If you're in grade 11, you should also consider writing the senior, because they'll also ask you, did you write CDC senior in grade 11 as well? So 11 and 12, try to go for senior. Even if your score isn't that well, at least you can put it on the AIF, right? Yeah, so that's that. I'm just going to show you a junior problem because this one's a little bit simpler to explain. Well, they always like to make these random names for these sequences, or like for math problems. So in a sumac sequence, which is just a random sequence, if you search this up online, it doesn't exist. They just made it up. Like the CMC people have very good creativity skills. So it's T1, T2, all the way to Tm. Each integer is an integer greater than equals 0. Also, each term, starting with the third, is the difference of the preceding two terms. That is t at n plus 2 equals t at n minus t at n plus 1 for all n greater than equal to 1. The sequence terminates at t at m if t at m minus 1 is less than t at m. So every number must be greater than, terminates at t at m, or if t, yeah, every number must be smaller than the previous number, right, in the sequence. And it terminates if the number is greater than your previous number, right? So you see that this is monotonously decreasing. 120, 71, 49, 22. And once you hit 27, right, which you get from 49 minus 22, once that is greater than the previous term, you just terminate, right? So this is a sumac sequence of length 5 because there's 5 numbers in it. And they'll give you the input, which is 2 positive numbers, T1 and T2. And the output would be the length of the sumac sequence given by the starting numbers T1 and T2, right? So they give you the first 2 terms, and you have to determine how long this continues until one of the terms is greater than the previous term, and then you terminate. So you can do this iteratively, so you can use an array to store the results. And this is quite trivial, but I want you to practice your recursion skills and try to solve this problem using recursion, right? I'll just get you guys started. So I'm going to write in Java because this is CP Java. Well, I'll keep this, oh yikes. I'll keep this open in a separate tab. So first, we know that we need to create a scanner. Let's read in the 2 numbers that they're giving us. So this is T1, right? T1 equals in.maxint. Let's read in T2, which is the next number we're going to read. All right, so how can we use recursion to solve this? Let's create a function called, let's call it f, you know. Like, it's not very descriptive, but I can't think of a good name for it. In competitive programming, you don't have to care about how your variables are named. Just name them like something that you would remember, right? You can name it A, B, C, D, E, F. You can forget all the coding conventions like comments and stuff because they're just time consuming. And you shouldn't do that in a contest. But if you're doing like grade 11 and 12 computer science, you better watch out for that. All right, so I have this f here, right? And I'm going to return, let's say f at a and b returns the length of the sumac sequence that starts with a and b. So I have int a and int b. Well, how did I come up with this statement? Well, I literally just defined it the way that the problem defined it, right? We want to find out the length of the sumac sequence that starts with A and B, right? So I'm literally just solving the problem within this function. So what would be my recursive call, right? I might need if statements in this case. So what is the base case? When does the sumac sequence stop? When does the sumac sequence stop? What's the base case? B greater than A. Yeah, so because B comes after A, well, if B is greater than A, then we know that we need to stop, right? Because it said here, if Tm, which is B, is greater than A, which is Tm minus 1, then we stop. The sequence just terminates. So what do we return? Imagine they just gave you A and B, and like T2, which is and B is already greater than A, then what do you return? What do I return here? If B is already greater than A, then what do I return? 2, exactly. Here, I'm actually going to say something like, actually, in this case, just to make our recursion easier, I'm going to return 0, and I'm going to call FAB plus 2. And you'll see why, because it'll help out a lot with the recursion. Because we don't need this 2 because 2 is going to be the answer no matter what, right? If B is already greater than A, then the answer is still 2, right? So this can just be the length of a Seubach sequence that starts with A and B, excluding like the initial length, right? This will help a lot out with the recursion later. So 2 is there no matter what, right? So we're going to get no additional sequences if B is greater than A. So we just return 0, right? What happens if B is less than or equal to A? What do we do now? What do we return here? F at B, A minus B. Precisely. Very good. We'll return F, B, A minus B. What else do we have to do? Remember, we're returning an int, and the int is the length of the Seubach sequence that starts with A and B. So what happens if we discover a new term in the Seubach sequence? What happens to a length? +1, exactly. So this just means the length of anything that starts with B and A minus B +1, because we know that there's an additional term. All right, this is great. Let's submit it. Let's see if it works. It better work. Whoops, what did I do? Oh, because I named it differently. This should be A and this should be B. Beginner mistakes. Yeah, so we got it all right. Congratulations. You might be wondering, would dynamic programming help in this case? Well, it doesn't seem like it would help, because it won't call the same, because there's like, it won't call the same like answer twice, I don't think. But if you wanted to do dynamic programming, you can do like something like int dp equals new int, like, what did it go up to? 10,000. Oh, that wouldn't be good, because you're going to get MOE, right? But in some problems, you might have to save the results, right? So in this problem, I would do something like this. But this was MLE, because this is not a dynamic programming question. But if it was a dynamic programming question, I could do something like dp at A at B equals to this, right? And if I've seen this one before, dp at A at B, if it's not equal to 0, then I would return it. So if it was a dynamic programming question, I could do this. And if Gmsh had actually had enough memory, I would still get the correct answer by doing this. This is basically saving the results, right? I literally have like a 2D array to store all of the results. And then if I reach that, then I would just return the previous answer. So that's how you can apply dynamic programming to these kinds of questions. However, this problem is a J3. It doesn't need dynamic programming. And you're going to run out of memory anyways. So yeah, so that's a basic recursion problem. You guys can also try out these problems. If you're also comfortable with strings, I would try out using bananas. And also this problem called mouse journey, right? Should I teach this? All right. This is the easiest S5 that has ever been done in CCC history. If you did the 2012 CCC, you probably would have done very well. But this was before they used computers to grade the results, right? They used to do it by hand. That's why the test cases are really easy. So let's say you are a mouse that lives in a cage in a large laboratory. The laboratory is composed of one rectangular grid of square cages with R rows and C columns, right? And if you want to get your exercise, you can move between cages. You can move right, or you can move down, and you cannot move diagonally left or up. So your cage is at one corner of the laboratory, which is 1, 1, right? And you want to go to RC. So you basically want to go from the top left to the bottom right in a grid, right? And your brother who loves numbers would like to know how many paths there are between your cage and his that do not pass through any cat cage. Write a program to compute the number of cat-free paths. So let's try this out. We'll create Google Docs. And let's try to model this. So this is CCC 12S5 mouse journey. So here I have R and C. So R equals 2, C equals 3. So that's what we have. We have 2 rows and 3 columns, but I'm going to mark them up so you can see the indexes 0, 1, 2, and 0, 1, right? And where's the cat? I have a cat in 2, 1. So I have a cat in, wait, is it, oh, 1, 1, okay. So if it's at 2, 1, then it's at 1, 0 in our grid. I have a cat. Okay, you can't come from here. And you're right here, so you're, what? You're a mouse. And you want to come here. Go here. And what I want to know is how many ways can I get from here to here? This sounds like a math question because it's a math question. So how can we do this, right? How can we get from here all the way to here? And how many ways can we do it? Well, let's think about how we can use recursion to solve this problem, right? So let's say I have a function called public static int f, right? What do I have to pass in f? Well, I need to know the location of the grid, right? So int r and int c. And what does it return? Well, it returns number of ways to get from r at 0 at 0 to r at 1 and 2, right? This is basically solving the problem, right? That's what we want to do in a recursive statement. So f at r and c returns the number of ways to get from r at 0, 0 to r at rc. So what's your answer? Well, your answer would just be equal to f at 1 and 2, which is number of ways to get from 0, 0 to 1, 2, right? So how can we get, how do we calculate f at int r and int c? How do we calculate this? What is this equal to, right? What's our return statement? So you might be really puzzled, like, how do I calculate the number of ways to get from here to here, right? How can I do this? Well, there's recursion, right? Think about this. You can only travel from down or right. So how can I get to 1, 2? What are the 2 cells that I can get to here? Right, Eric got the right answer. So it would be the number of ways you can come from the left and the number of ways you can come from the top, right? So I can do f at r and c would be equal to f at r minus 1c plus f at rc minus 1. I'm just going to call this ways because that's more representative, right? Ways to get to r and c is the number of ways to get to here plus the number of ways I can get to here. Right? Do you guys kind of see this? So how to get to here is the number of ways I can come from here and the number of ways I can come from here. And they can't overlap because they can only go right or down. So for example, how many I have, what's the base case here? What's the base case? So we know that there's only one way. Yeah, so Eric got that right, base case. So if R equals 0, and I'm just not using correct code conventions, but if R equals 0 and C equals 0, right, then I would just return 1, because there's only one way. There's one way to get to 0, 0, because he's already there, right? How can he get there? By not moving. So he has one way to get to here, right? Well, how many ways can he get to here? Well, he can either come from the top, which doesn't make sense because there's nothing at the top, or he can come from the left, right? So I can put 1 here, right? How many ways can I get from here, get to 0, 2? Well, I can come from the left or I can come from the top. Well, there's only one way to get here because you can't come from the top, so it's 1. How many ways can I get here? 0, because I don't want to touch the cat, right? I'm a mouse, I don't want to get eaten. How many ways can I get here? Well, I can come from the top or I can come from the left. Well, left is 0 because there's a cat there, right? So it's just left plus top, which is 1. Well, how many ways can I get here? Well, I can either come from the top where there's one way to get to the cell, right? So there's 1. And I can come from the left as well. So 1 plus 1 equals 2. So in total, there's 2 ways to get from here all the way to here, which is the right answer. There's only 2 ways, right? You can either come from the top or you can come from the left. And also, there's 2 ways to do this problem. You can use a loop, like literally looping through a 2D array and filling it out using the algorithm that I just said, or you can do it recursively, like this, right? If R equals 0, we learned that we can only come from C minus 1, right? And if C equals 0, well, you can't come from left because there's nothing on the left. You will just return ways at R minus 1 C, right? And now you have your answer. You would just write this function and you'll solve the problem. So yeah, recursion can get really abstract, right? But you just have to think about defining your function, right? What kind of information do I need to solve the problem? I need to know their grid location. So I need to pass that into the parameters. What do I return? Well, I return the answer, right? The number of ways to get from 0, 0 to R at C, right? And then you think about how you can reach this, how you can reach ways at R and C. Well, I can come from the top or I can come from the left, right? And how do I relate the two? Well, it's the sum of the ways that I can reach here and the sum of the ways I can reach here. So that's how you can solve most journey. It's a dynamic programming problem. Don't worry if you didn't get that. Most of the junior problems don't require dynamic programming, but if you're doing the senior, you can brush up on your dynamic programming, practice a lot of recursion problems, and save the results in like an array. Yeah, so that's pretty much the end of today's lesson. I hope you guys practice a lot of DMOS problems because there's a lot of contests that are happening and they're great practice. And don't give up. Like if you mess up like a contest, like just keep going and learn from it. To redo the problems that you didn't get in the contest, read the editorials. The editorials are the solution to the problems that other people have created and try to understand them. Are there more topics in the CCC senior that we haven't covered? Lots. There's lots of topics. What will most benefit you is to learn something called graph theory. We're going to be taking a look at some graph theory questions next
After
week.
another person.
Yeah, well, I don't know a lot of people with a last name of theory, but search that up. You can learn about
maybe. Maybe.
Maybe. Okay. I never actually searched that. But adjacency list is something you can search up. And DFS and BFS. And BFS is not best friends. It's breadth first search. So you guys can study these topics. There's definitely one question related to graph theory in the senior. And there's usually one dynamic programming question, like the ones we took a look at today, using recursion and saving the results in a table. There's other stuff. There's other data structures, right? So there's things called segment trees, right? And there's things called binary index trees. So there's lots of topics we haven't covered simply because we didn't have enough time, right? Since we learned prefix sum arrays in a previous lesson, you'll understand why we need segment trees. Like think about what was the bad thing about the prefix sum array and the difference array. It's that we had to loop through the entire array every single time we wanted to find out the value at a specific index, right? Or like update it. So segment trees, you can learn that. Binary index trees, you can learn that as well. What other topics? You can learn monotonic stack and queue, which is an interesting application of stacks and queues to solve certain types of problems. String hashing. If you look at the S3 from 2020, you came across a string hashing problem. What string hashing is you're converting a string into a number. So if you ever wondered how a hash map worked, which we learned in lesson 3, it's basically converting your string or your object into a number that it stores at an array location, right? So string hashing teaches you how to convert a string into a number. And make sure that and the good thing about turning a string into a number is that it doesn't have to compare two strings character by character, right? So if I wanted to know if two strings was equal, what I would traditionally do is to compare like the first characters. If they're the same, I'll compare the second characters. If they're the same, I'll compare the third characters, right? To see if they're the same string. But what if I had like 1 million strings? Then how many comparisons you have to make? You have to do 1 million squared number of you will need to do like a ton of computations, right? And you don't want to do that. If you compare two numbers, it's just one calculation, right? Is 1 equal to 2? No, right? Is 1 equal to 1? Yes, right? So you convert each string into a unique number, right? So if I gave you apple, then you will convert it into 1 using an algorithm called hashing. And then if I gave you apple again, you will convert it into 1. And I want to see if these two strings that hold apple would equal to each other. I just have to compare, is 1 equal to 1? Then yes, then that was very efficient, right? So you can learn string hashing. You can learn segment trees or binary index trees, but they're not too relevant. I haven't seen a lot of problems that use segment trees and binary index trees, but definitely learn graph theory. What is an adjacency list and what is DFS and BFS. And since we taught you recursion today, DFS should be pretty easy to understand. Graph theory concerns itself with how you can get from one location to another, right? So graph theory, you can model like a series of paths, right? Like for example, Google Maps is a graph, right? It's a network of roads where your car can travel, right? So how does Google Maps calculate the shortest distance between my house to pet, right? So that is something that you will learn in graph theory if you look it up. Like look up some YouTube videos to learn graph theory. I'll actually search up some YouTube videos that might be helpful. Oh, this one's good. I'll paste the link in the chat. This guy does a pretty good job of explaining the graph algorithms. Just learn adjacency lists and what is DFS and DFS. There's also this really good website called Geeks for Geeks. You can also learn graphing algorithms there. There's another website called CP Algorithms, but it's more complicated. So if you have a good foundation in mathematics and you understand all of that fancy mathematical notation, you can go to cpalgorithms.com. It used to be a Russian site, but someone translated it. Yeah, so those are all the resources. So brush up on some graph theory. Next week, we're going to merge CP Java and CP Python. We're just going to explain the concepts of how to solve some of the 2018 and 2020 problems on both the senior and the junior. And I hope you guys all come because it's going to be an interesting meeting. Thank you guys for coming.